Hello, welcome to episode 5, Hyperstition broadcast. Yesterday we had a great conversation on the mathematical and experimental framing of this so-called Einstein-Podolsky-Rosen paradox and its connection to Bell's theorem, which is measuring certain mathematical correlations with experiments determining weird things, like is reality actually there when you're not looking, or can information reach you from the past? And I think there's been lots of discussions on this topic, people leading to the point where they say, yes, we live in an information theoretic universe that is the base layer of reality, and we are observers, and we just select one possible, path through that state space. But it's always been framed very broadly. And I think, so today's conversation is going to be very interesting. It's someone who's actually approached this from a very grounded, rigorous mathematical perspective, and produced a new work called Observer Theory. So it's Samson Chal, and he has an interesting background where he actually, not an academic kind of guy, but instead built a couple companies that were very successful, runs a fund, but has more recently gone into the world of this independent research and is here to present his Observer Theory with us. So, hey, Sam, thanks for joining us. Appreciate it.
Hey, thanks for having me, Andrew. I really appreciate it. So what I'm going to present today is sort of abridged form of a presentation that I gave to Michael Levin's Platonic Symposium, but this covers observer theory. And just for some background, this paper K is built on some of the work from on a minimal observer model by Xerxes Arsiwala at the Wolfram Physics Project, and this extends it to look at observers all the way up and down, so a universal model, and it really is discussing the implications of that sort of model. So what is variable and what is invariant within an observer theoretic model, which is important particularly for materialists, because they care about things being the same everywhere. And I think the interesting thing for me about this work is that when you construct a sort of formal observer model, you can start to say things about everything, because what you classify as an observer is something with a persistent boundary that's persistently sampling some possibility space, here a computational possibility space, and that lets you sort of draw long chains. And I think that's quite important, and it's quite a sort of convergent model where every single type of observer is doing the same thing. They're just doing it with different computational power, different persistence in time, and therefore different agency or different choice between states. So I'm going to kick off and just set the scene for you, because I think it's important to give.
I think that's like a great, just for how you framed it, because I think, experimental measurements, we talk about these as observations, but this is like a laser interacting with an atom or something. Whereas we as observers, our level of experience, we think of that as observation, but it seems very divorced from this like context in which you'd measure these more esoteric physical phenomena. So it's kind of putting those in the same context, in the same framework.
Exactly. And like bluntly, like, why should it be different? It should just be more complicated, right? It should just be more complex, or there should be more going on. But like a model of observation and measurement, I mean, why would it be different for, a laser measuring a pen? Like, why would the loop be different? So I agree with you. And I think that's I think it's one of the more underdetermined parts of certainly philosophy of science, maybe even like empirical science, that seems to very much matter. And I mean, there have been quite famous experiments on Hilbert spaces where they take out the observer and it's trivial outcomes. It seems like physics requires it. It seems like physics requires it, but yet the theories we have, and this is not to denigrate some unbelievable work by many people much, much smarter than me, it's just very narrow. And I think the innovation of Wolfram's sort of meta model, the Ruliad, this space of all possible computations, it's entangled, it's all joined together. Every diagram commutes, like every path finds a limit, you get an output. That sort of structure enables you to say more. And this is the attempt at saying more. So I'm going to, again, Andrew, interrupt me, questions, I'm not sure. I'm going to work through setting the scene, which sort of talks about the background objects, and we'll work through that, and then we'll work through some of the implications and how I'm using it to sort of explain phenomena, because this is meant to be an explanatory theory.
Excellent.
Okay. So just to give you the background object, look, there's tons of work online about this, and highly recommend reading Stephen's blog posts and essays and the long list of papers that really formalize this and take this idea. But the Ruliad is sort of your maximal computational state space, your maximum possibility space. It's where it's an everything computation, all possible computations, all possible systems. And here it's an abstract mathematical object, but we're using it as ontologically real, as like a basis, as like a information centric dimension where everything else filters down. And this object is not the universe. It's like every possible multiverse can be modeled in it. And that is quite a unique thing, because it has all this branchial space, these multi-computations at the bottom of the slide. That's like, every sideways computation is like a new branch. And then you have time and causal time, which is, our clock ticks.
So this is kind of like all mathematically possible universes, I guess, or something.
Well, like all computationally possible universes. So I think the key thing to say is I'm not as hardcore a computationist as Stephen, right? But I do, and where Stephen thinks everything, and I'm going to use the Trump language, everything computer, right? Like, though Stephen would say it much more elegantly than that. I think that computation is the biggest possible tool we have to model anything. And therefore, every possible model that we do in science should fit into a computational framework, which is why this meta model, this structure, is so powerful. And so that lets you model our universe to an arbitrary accuracy in this structure, given enough computational power and enough memory. So that's just a nuanced point, because I've had some critiques for the thing, because this talk says things about the structure of conscious experience, where people say to me, oh, well, we're clearly not just doing binary computation. And I'm like, yeah, we're not, but my personal view is we're not, but the way we can describe it is that way.
Right.
And so that's, I think that's the key point, right? So this is still coarse grained to what the actual thing is, but this is a process-based model, and so hopefully we can go from there. So I guess here I just want to frame computation and the way I think about it within the Ruliad. It's cause and effect processes, input, function, output, in every iteration it can possibly be. And I think the other point that's quite important is computational observer models, what's invariant versus variant. And sort of the causal structures are independent. The underlying structure of possibility space and latent space is independent of the observer. It's just there. And the computational samplings, i.e. when we take a slice or we take a snapshot of that space, they are variable. They are variable depending on the observer and their boundedness, their persistence, and what they deem relevant. And the other thing that is invariant are the categorical relationships. So the formalism for the Ruliad was designed by Xerxes Arsiwala and Jonathan Gorard a few years ago. It's what's called an infinite groupoid, which is basically, imagine an infinitely stacked pancake, right? And each layer is like a dimension, and there's lines going up and down, and it all comes together to form a closed topology, which means you can output, and this is what the Wolfram physics do, they output geometry, then math, then physics from it. And so without it being a closed structure, you can't really do that. And that's the sort of category theoretic part of this model, which we can get into and is detailed more in the paper, but I'll try and keep this sort of relatively plain languaged. So here, what is an observer? What are we defining an observer as? And I mean, the tautology as an observer is something that observes, but here, I think the most important thing to say as an observer, between hypergraph updates, so this is a discrete model, we have state 1 and state 2 to state n, that boundary around the observer is persistent. They are doing computations within a boundary with an internal model or some minimal internal model, but that boundary is persistent between hypergraph updates, so they have a persistent thread of causal experience. And this goes from the most minimal, like a molecule or an atom, to us. So and even above us to superstructures like societies and economies and politics. You can apply this model to all of those types of objects. And really this model's about causal influence. So here the function is observers are sampling information from possibility space. They update their internal state and output actions. This is a cybernetic model. This is actually second order cybernetic because the observer is embedded within the system. But because each observer is finite, they have limited computational resources, the slice they carve out, the coarse grain from this gigantic infinite structure, is their experience reality. And this is due to those two metrics, boundedness and persistence, which are like the core determinants of how big the observer's boundary is and how long it lasts for. And you have an observer acting like a sort of lens or a filter, simplifying the Ruliad, finding, repeatable, computationally reducible structure. And that finding of that is determined by a relevance predicate within the function of how an observer works.
Okay. So on this boundary thing, it seems like if a civilization can count in this same framework, the boundary around that seems hazier than like the boundary of an individual would have senses, whereas a civilization has like this constant flux of things at the boundary. But I guess, does this mean
maybe, but then how long does the average human last? 80, 90 years, maybe 100? How long have some civilizations lasted? So
I guess the point I'm making here is the boundary is an arbitrary cut you're making around some subset of nodes in this hypergraph or something like that. Like it's not actually like I'm in flux with my environment, my atoms are being exchanged and stuff.
Correct. Yeah, correct. This is the correct way to think about it. So imagine your internal model for a second, and who is Andrew? Andrew, you look in the mirror, you see Andrew. A civilization might move around a bit more at the edges. So the structure and what that civilization stands for, what defines it objectively in that computation might vary, but there'll be some sort of irreducible core that defines that civilization. Otherwise, it's not that civilization. It's not civilization A, it's civilization B. So there's only, it's like an elastic band, right? You can only pull it so far before it becomes something else to other observers who are recognizing it, right? This is all coupled, right? So a civilization is built from many sub-observers. So not just you, but, let's call it the courts in that, like the courts, the army. So there are lots of observers all pointing in one direction in the Ruliad, and that boundary, that like circle is around them, and say someone at the edge of that boundary might point somewhere else. You get Julius Caesar, and suddenly the Roman Empire changes from Senate to emperor, right? But because the internal structure is still a lot of Roman things, you would still recognize it as Roman civilization, even though it's like a fork, right? And that's I think a nice sort of computer science analogy for it. It's like a sort of small forkings, you keep the code the same. Big dramatic forking, you got a new thing. And that's sort of the sort of way to frame it. So just to work on the observer loop. So on the left-hand side, the claim here of observer theory is every possible observer, everything we can define as an observer, from atoms to human civilizations, implements an identical loop at basically different speeds, right? So I put it in plain English on the left: sense, integrate, evaluate, select what action you're taking from your possible actions, then act, and update your model internally, then network and share that with observers in your neighborhood, i.e. who you have causal contact with through a node in the hypergraph, and then repeat. It's pretty simple. Just to give some link to the formalism for the minimal observer model, this is mapped as a tuple in the RC Waller formalism. So, I stated it in the middle: state space, input space, and an output space, and some functions that map between them. And then on the right-hand side, I'm just taking you through the plain English translation back to that so that you can see the sort of see how it converges. So when sort of an observer senses, they're restricting this big Ruliad to relevant inputs, and this is part of that relevance predicate, a Boolean that is in the observer's functionality. So boundedness, persistence, and relevance. And relevance is determining what they restrict. Integrate, they update their internal state and try and compress those inputs, i.e. find pockets of computational reducibility to put that into their internal model. They evaluate, they compute the predicted value or utility in there. You can slot in, different theories of how we do that. So FEP is a good example of a theory that would potentially slot in there. And, this has been presented at the sort of more formal category theoretic version was presented at the Active Inference Symposium in November. And I think presenting this to Carl's theoretical working group, mostly because that measure is probabilistic and this measure should be in bits. So it's deterministic. And that means that it's quite helpful to have that discussion with their team. And then select is choosing an action. And here observer theory makes a claim that all observers have some non-trivial telos, i.e. they are maximizers or minimizers of something. And here the position in the paper is that it's integrated information, it's structured information, it's useful information that they're maximizing at all scales. Then they act, they change their environment. By acting, they update their future inputs because they get feedback from the environment. And then they update their internal model and adjust for that prediction error, for that surprisal that they may have in their selection, in their evaluation. And then they network, exchange it with other observers that are impacted or are impacted by their decision in the local neighborhood, i.e. where they causally touch. And then it just iterates through time. So it's an iterative loop, keeps going forever at every possible scale. So I just want to define a couple of other things. So the field of observation is a smaller subset of the total accessible Ruliad for an observer. So if you think about it as sort of three nested circles, you have the biggest circle is the entire Ruliad. This is a huge space where we access barely any of it. Then we have a sort of middle circle called the observable Ruliad, which is the limit of what observers can possibly, or observers defined this way, observers like us can possibly access of that entire Ruliad. That's with R with a subscript O, observable Ruliad. And then you have this small pink circle on the pink cone, which is what we're focusing on right now. So this is the part of the observable Ruliad that we're sampling now between hypergraph updates. And this is the part where this is the sort of set of states an observer is integrating information about or over in that between hypergraph updates, so the function part. And this is constrained by current computational boundedness and your current persistent and your observer judgment of relevance at that point in time based on your causal history. The difference between that and the observable Ruliad at the limit is that is minimum computational boundedness given whatever constraints an observer has, and maximal computational persistence, i.e. how long they could possibly last for. So one space is bigger than the other. We're doing work over the smaller space. Now, the interesting...
Just to frame it here, because I think there's a lot that's been, I want to like kind of cement, get a checkpoint in our conceptual understanding. Okay, so we have this Ruliad. It is the space of all possible computations. It's described by the structure we call the hypergraph. We take observers to be kind of bounded collections within this that are sort of coherent information processing units. These have some kind of internal update model that's going through this. Basically, it's kind of like this, you know, observe, orient, act, decide, exchange kind of update model, right? Now this Correct. Is saying it's like my observerness. For me, this is kind of like what's my context window in some sense. It's like how much of
it's a good way to think about it.
How much of the Ruliad, how much of the possible, the computational space am I observing or integrating information? There's like this maximum possible limit, which is perhaps like I have like, you know, like the X-Men, like the helmet on, and I'm like in this thing, and like it's, you know, psychically connecting with everyone.
Yeah, I'm a comic book nerd, so yeah, I get it.
And then on the other extreme, I'm like hungover and I can barely like pay attention to anything or something like that. This is kind of what you're getting at. It's like how much of our computational...
How much of reality are we getting access to is the nice way to say it.
Yeah,
so the interesting thing is, you know, why have I set a limit space and sort of an action space here? The interesting thing is that it really applies to observers like us most of all, but your belief system or what you believe in can imply a different size or limit of that accessible possibility space. And so that's, you know, so why is there a link in observer theory to theology? Because theology is as a limit space. Like if you believe in like, you know, this transcendental panentheistic God, right? Well, that's massive, right?
Mm-hmm.
Maybe, you know, that's the biggest thing we've invented, right? At least, you know, I think it's the biggest object we've invented, if we've invented it or if we're discovering it, question mark. But, you know, it's something that if you were an atheist, you say, we've invented this thing. Why do we have religions? They have utility. They give us a bigger limit space. right? Like, so it explains why things survive and also why religions evolve, right? Why don't we have animism or polytheisms today? Because they're smaller state spaces than big God, right? Like that's the, so you get interesting ideas, like there's interesting ideas around the dynamics, and this also applies to mimetic evolution, right? So you can apply this to like ideas as well at a sort of smaller scale. And so that sort of thing, like our beliefs become quite important. Like, and beliefs are not necessarily just things that live in the realm of religion, you know, and maybe a bunch of physicists will kill me for saying this, but axioms are, you know, effectively beliefs. Like, okay, they're scientific beliefs and they try to adjust them and make them smaller or come up with new ones, but they're beliefs with utility, right? Like, you know, a Hamiltonian space does not actually exist. Like, this is not a real thing. Like, you know, this is a classic thing. It has lots of utility. It makes the space of things we can observe bigger, therefore we utilize it. And so that's just the sort of the corollary I want to draw for any materialists who are, you know, smacking their screens right now, because this is often not, you know, this is kind of, you know, an argument of certainly something like monism or dual aspect monism, you know, here that we're, you know, we have dual aspect monism, we have some informational substrate, and we have an observer that's part of that, and they're sampling, right? So it's not materialist in the classic sense, but it's also not idealist, because it says, you know, the physical world is real. So I just want to make that clear. I think one of the interesting things that came out of the category theoretic formalism for this, and certainly the extension, was the idea of top-down and bottom-up causation. Now, there has been, after I published the May paper, it's like unbelievably bright and pretty brilliant research called Eric Hoyle published a paper called Causal Emergence. And causal emergence is basically trying to empirically measure macro scale or top-down causation versus bottom-up efficient causation. So, and that has now been shown to be at least empirically validated as top-down causation can exist without breaking physics. But this is in this as well, right? So causation here is a state transition in the Ruliad. And just for observers like us, a mental and a physical state are part of the same sort of joined up map, the same overall structure. Your thought is a thought you might have, or a sentence you might say, is a computation or can be modeled computationally in the Ruliad, as can a particle. And because this map is one joined up thing, they must exist in the same structure. And the interesting thing about the formalism is these can be mapped with functors. So you can model top down and bottom up causation in this without breaking causal closure in physics. And that is, again, another, I think, unique thing about the Ruliad as sort of a backdrop model compared to sort of other formalisms or just physics formalisms or, you know, just assembly theory. It's just a bigger space that lets us do these things. So
a question on that. This Ruliad, because you mentioned this hypergraph update and also this state transition or state change. Are we thinking of this as like some graph that is like the whole thing is incrementing in time somehow, like from one time step to another, and it like
yeah, think about it in terms of computational time. Just think about it: time step 1, time step 2, time step 3, time step 4. Now, in the Wolfram Physics project, and they I think have this on their website, they have mapped in their view, and it's very speculative, how many sort of how often in actual time the hypergraph updates in our physical universe. Yeah. But you know, that I can't remember the number off the top of my head, but it's really very, 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 very tiny. I think it's, you know, even sub-Planck time. But you go up to us, and really what we're talking about is the resolution of our snapshots. So even we have a hard physical limit before things decohere to an observer like us, right? We get to Planck time, and you're a smush in a cloud, and so am I. But we don't sample at the same rate. So our experiential time is slightly different to the hypergraph update time, right? So we're not you know, many hypergraph update steps constitute one observable time step for an observer like us. Does that help? Yeah.
A little bit, yeah. I'm just, in your thinking, like this hypergraph, is it an observer or a collection of observers? Are they traversing through it in some way? Is it like, is the hypergraph structure itself refer to some fixed set of things, or is this the overall graph structure, connectivity and stuff like that is evolving in time?
The overall graph structure is evolving in time.
Okay, cool.
So, but the observer's embedded within it, so that's also evolving in time.
Yeah.
I don't think they're actually, you know, if you're a bundle of computations, a persistent bundle of computations, well, you're in a network, right? Like Indra's net, you're not moving, but where you're pointing is giving you that suggestion of movement because the hypergraph's moving around you. Does that make sense?
Yeah. And then does that connect to this like topological closure? Like all nodes are connected to all other nodes through some traversal thing?
So that's just a function of the type of topology in the formalism. So an infinite groupoid has a compactifying point at infinity. What that means is with infinite time, every diagram commutes. There's a closure point which has all of the causal history. So imagine running it through time, running it through hypergraph updates, and at some point in infinity time, every computation completes, right? So every computation finds its endpoint, and that all composes to one point. And that point is the endpoint of computation, right? We in Stephen's infinite computational universe, which is countably infinite, we have done all the computations in every possible way, and that's that point. And so that point is an absorbing state. It has clearly got all of the causal histories of the entire structure in it through from beginning. It therefore has, and the reason it's useful here is because it does a couple of things, right? It avoids infinite regress in observer models. So like naive models, like, turtles all the way down is the classic line, right? Because this says this structure closes, there's always a way for an observer to close a computational loop, even if they can't reach it in finite time, even if it's outside of their boundedness. Every computation, imagine a maximal observer, is tractable in this structure. And so that really helps when you, again, it's not really, I don't think it matters so much from the philosophy side or sort of some of the stuff we're talking about for observers like us, but for physics, for Wolfram to have this model as a physics model, it matters enormously, because without it, you can't do anything. You have no geometry. You have no building block from your minimal rules to build the spaces that you need to do physics. So you have to have this sort of closure. And maybe I'm extracting more than maybe what Jonathan and Xerxes wanted to give with it, because it is, very much a proven mathematical object. So this is more like I'm applying it and saying, well, if I run that through in time and actually think about what that point represents computationally and informationally, and then I run it back, what does that enable me to do in an observer model? So that's the sort of way it's being utilized here. And I think the one thing I want to say about formal or efficient cause in here is that observer theory, we create a domain structure, and domains are determined by the amount of rules an observer has to sample within that domain to output a persistent object. So formal causation is less constrained, i.e. less rule-bound domain sampling, influencing or setting the state space for the efficient causation that comes back up from the feedback from the environment. So more rules for efficient causation, less rules for formal causation. One sets a space, one gives feedback to that space. And that is detailed with functions or in the paper, but I just wanted to give you sort of an idea of how this works. And again, to see that empirically, causal emergence, I think it's 2.0 or 3.0 is on now. It's on arXiv. It's a great paper, and does this with real empirical results to show this is possible. So I'm going to move on to some implications of this sort of idea, because I think that's really the interesting part. Like, spend 50 pages talking about the formalism, but it's really the implications that get me interested in this idea and really where I came in it from. So I think, I think the title Observers Away already says it all. And I'm taking a step back to physics and going, well, if I have this observer theoretic model, what does it add to sort of a latent space, or in Michael Levin's language, platonic space and ingression? What does it add to the picture? And I think the three moves here are, we treat pretty much everything that's persistent in time as an observer. And so consciousness, and this is kind of, it's kind of panpsychist. So if you think about panpsychism, they're like, consciousness is everything. But consciousness as a word, at least until maybe even the last 10 years, was really sort of a very anthropomorphic word. And only in the last 10 years have you gone to like animals and, I think, Gaia books, maybe plants as well. But where does that line stop? And they're smaller, like it's exponentially less than us, right? Like an animal has exponentially less access to experience than us because they don't have language and no sort of metacognition. Plant in, an exponentially lower amount. Where does that line stop? And here I'm kind of drawing the line and saying it has to be persistent in time, right? So I've modeled an atom as the minimal observer here. Maybe it could be a proton, maybe it could be a neutron. I was just more confident in saying an atom as sort of first start point, but that could change. I think the other point to make, and this is related to a paper that came out a couple of days ago, is the observer theory model talks about observers trying to maximize integrated information or structured information they sample. Now, if observers are bounded and this space sort of overall is computationally irreducible, they are trying to find and discover pockets of computational reducibility or pockets of predictivity. I get an input, the function runs, I always get the same output, or to 99.999999 so on % confidence, I get that output. But what do those things represent in a sort of topological network model? What are they? Well, here they're sort of objects, they're geometric objects. You're sampling a geometric object, a set of computations, and symmetrical ones save you computational power. Why? Because if you have a symmetry, I don't need the whole structure to calculate the whole structure. I only need a part of the structure. Just think about, calculating the area of a rectangle. If you cut it in two, you've cut it in two. If it's symmetrical, I know that it will give me the area for less compute, right? And that's the kind of framework. And these are constraints on what we can sample and compress. And then here, what I'm interpreting quantum fields as are the substrate on which observer relevant patterns are carved out. And again, this is kind of, I think, aligned with, but saying slightly more than someone like Chris Fields' decompositional equivalence observer model for quantum theory. This is really more general, and this is just saying, how do I frame an observer theoretic model in what we know is true in physics? And this is how I frame it. And so this is, why is this a reinterpretation? Well, it's just trying to connect observer constraints to emergence of complexity through time. And it's trying to offer sort of a through line from, the micro Wolfram physics project hypergraph updates that you're talking about to category theoretic observers, which is what the minimal model talks about, and this paper extends, to human superstructures. So big things that we talked about at the beginning: politics, economics, theology, society, sociology. And you can use AI language, like, you can think of like a tower hierarchy of agents, each with more power within a computational system. Same type of thing. And then on the right, I've just shown like how much information something can sample, right? So, you have the rules or like this minimal unit in the hypergraph, and then you get to particles that are persistent, and you get to sort of minimal observe. These things are both impersistent, like they don't stay in time. If I take a sampling of a part of space, the quantum foam will chuck out some quarks and gluons, some other stuff. But then I get to an atom, and that atom is always there, right? The same atoms are around. And then I get to, and that's kind of how I drew the line here. Though, someone smarter than me may be able to say, actually, this thing is also, doing non-trivial observation. So this is new.
Yeah, there's lots of interesting things these days. Whether you can have information embedded into like space and time itself or something like this. But this is cool, because it's basically saying, it's like, don't, observation, let's just really call it like physical field interactions. Like as this interaction mechanism, let's just call the observer anything that has some kind of persistent state over time, which could encode the result of these physical field interactions. And so molecules, yes, these have some kind of, I think this is making sense, yeah.
Yeah, and so you can and just to, we've done it here, right? So you can look at, the property of in the loop, right? And then does a hydrogen atom do it? Well, if it senses, it, absorbs photons, and as you said, it interacts with fields. It has an internal state, right? We know that. It has non-trivial action, right? An atom can emit a photon. It has a clear boundary, and it has a feedback loop. So those emitted photons alter their neighbors in that neighborhood for that atom and change the future environment. So the claim here is that trivial observation is not what I would call conscious in the panpsychist sense. So, I'm going to reframe panpsychism and say everything's observation, and humans or we're just self-referential, uber complex observers. And and consciousness is sort of this thing that kind of has scale, but do I think that a hydrogen atom is conscious in like the panpsychist word way that sort of someone like a Philip Goff might say? No. Like I think that you've got to treat it as what it is, right? Like I think they're too far apart to share the sort of word with us.
I think though I could see maybe this is the next slide, I don't know, but like the conversation I had yesterday was really, the Stern-Gerlach experiment where you have silver atoms getting split by their spin into different compositions, and you kind of prove that like there wasn't any these didn't have like an internal state representation independent of when you actually went and observed them, so I'm wondering like calling like atoms and their informational state as observers, but they are not, to us as observers or to the experimental apparatus, they look like they have this undefined until interacted with state, I guess. So I'm guessing there's probably.
I guess the only consideration, like the only sort of counter to that is atoms definitely existed before we existed and before certainly life existed, or so were they doing anything? And this is the question is not, the question is, can I frame the loop in this way to make it universal? Is it doing these things that are within the minimal model? And the answer is yes. Like, I feel like that question of whether we observe an internal state, that when we look at it from sort of up here in the observer hierarchy, again, exponentialization, exponential growth in capacity means that we might not be able to sample that internal state or that internal model as a limit of we're too far apart in Ruliad space, right? We are too far apart to see the internal loop there. It's too fine, right? We can't coarse grain it. We can't get to it. Our bounded computational power doesn't let us see that right now. And so that would be the sort of position that this paper would take on that. But it's a fair point, and this is, a very new theory and a very new paper that's been presented like 4 times. So I'm looking for those sorts of challenges, and I think it's valid and fair. Like I think it's a valid consideration for sure. So I'm going to move on to look at sort of structured information and unstructured information. So so what we see as randomness or noise and what we see as structure. And the observer theory position is that in this computational universe, symmetries represent something we can reduce, but breaking that symmetry at the edge of that line, that's at the edge of that structure, increases our distinguishable space, increases how much we can sample of it. And the analogy in the bottom half, and this is something probably relevant to like gravity, where they're trying to figure out there's no sort of there's always broken symmetry there. There's an analogy of like one configuration, high symmetry in a Rubik's cube, and then when you scramble it, you have many more configurations because that symmetry is broken. And wrapping that back to the Ruliad, symmetry breaking in R, an observer picks a branch, and therefore there are more fine-grained equivalence classes within that observable Ruliad, i.e. more objects, more structure they can find. And that's the sort of mapping back. And then, the reason that observer theory is interesting is because we've sort of grown our language through time, like our ways we can talk about things. But if this structure is universal, then we should see parallels all the way through time, albeit in poetic or metaphorical language. And like you can pick whichever tradition you want, like whether it doesn't have to be a religion, it can be a philosophy, it can be Plato, you can be Pythagoras, from the one to the many, right? Like this is the intuitive description, because observers are stuck in this structure and they can intuit things about it in some domain of information they sample. This is how computation, observation, and symmetries produce our structured universes. And these live in every tradition that you can go back thousands of years, right? So it's sort of drawing the line, because it should be self-similar to the structure, to the observer, to the minimal observer, even if the detail of what they're sticking in is different, or the fine graining of that structure, or the amount of depth they get, or the amount of predictability they get from that structure changes based on how much computation they have at that given time, right? So that's, I think, really a really interesting aside. I think the last point that I want to sort of talk about is this isn't kind of a reframing of other interpretations, right? I think this is kind of making a distinctive, put my neck out there, ready to get cut down by many more smart people prediction. So I think if we look at sort of these four sort of areas, and I pick big buckets, right? So many worlds is, this is a constructivist theory, right? It's really a constructivist theory at heart, but I disagree with many worlds. I think many worlds is incorrect, and I'm saying that to one of my academic heroes. I think it is wrong, and I think it's because selection is inbuilt in observation. If observers are sort of outputting physics, or the most efficient physics they can, they are selecting the branches in the computationally efficient way, and the branch weights within this network track that information integration, like that telos, and with a gradient, like a fitness landscape. And so it's not just an amplitude thing. It's like, we are picking the best of all possible worlds here. Like we are finding the fastest path. That is like a common thing across observers. And then versus something like Copenhagen, collapse is just an emergent description of observer bounded sampling. If you had an unbounded observer like a plus demon, they would not get collapse. They would only, it's because it's a constraint. It's a computational constraint. Again, materialism is, I think, is probably going to be shown to be very wrong very soon, but consciousness arises from randomness plus time plus emergence, finger in the air. And again, I might anger some materialists with that conception, but that is my sort of very high level takeaway. And
I don't think materialism survives like quantum mechanics. I think I think right away, like yesterday we got, it's like,
I was corresponding with a very famous cover of Nature scientist with a very, very, very strong constructivist theory. And I was having an email chain with him. I was talking about this, because I've spoken about observer theory before. And he was like, and his questions were like, unless I can put it in a lab, unless I can put it in an experiment, it's not real, it's not interesting, it's not useful. And I'm just like, but your theory is literally like a subset of this space. Like, how can you possibly say that? People, I think, there's a famous line in science that kind of philosophical attitudes change one death at a time, or one major death at a time.
Yes, certainly.
And I think that's kind of probably happening over the next 10 or 20 years. And I think here the difference between materialism is saying that observers sample different domains of information, and consciousness requires a threshold of integrated information across all the possible domains that we can stratify the structure in. And so not all computation or observation can qualify for that word. If you want to extend the word, fine, I'm not going to stop you, but that would be my sort of position on it. And then sort of versus idealism, like someone like Bernardo Castro, mind is everything. I think we see stuff, we touch stuff. I don't think this body is a fake body. I think we are embodied. But here we're saying they're perspectival slices of a single computational structure, and that the information is the fundamental part. Its instantiation is secondary. And that's, I think, the sort of major differences with some of the other philosophical ways of looking at physics or looking at QM.
Yeah, so I want to pause on that, because I think that's one of the, when I read the more extended paper, I thought that's one of the things that got me thinking, was it kind of puts what we think of as cognition, concepts, this platonic realm of ideas, maybe emotional states and stuff like this, into a similar, somewhat equivalent framework as what we think of as conventional physical reality, where it's there's physics to describe how molecules and stuff behave, but there may also be a kind of physics of psychology, a kind of physics of reasoning or something that is
exactly, nail on the head. Though I would use computation over the word physics, because I think physics is a hard, it has so much baggage. Sure. It's kind of if I can model, if computational physics is a valid model, right? And I think it's probably if and only if computational models of physics are valid, then I can extend that computational model in a coarse-grained fashion to valuational things, so emotions, to reasoning things and logic, like language, and maybe even all the way up to archetypal structures, or big structures that have long-range entanglements in the structure. So stuff with lots of causal influence, right? this could be a Jungian archetype or a story structure or something.
Yeah.
Like, what do mathematicians say on the weekend? I'm a Platonist. I'm a mathematical Platonist. The form of this and they always picture things. It's never, they don't see the formula, they see the thing. And there's a classic, like, what's his name, Raman Jan story where he sees like the red waterfall when he's having a dream. And, like, are these structures like, is the structure of a circle, which has causal influence on pretty much everything below it, does that exist in some minimally constrained space where the entanglement is literally just a giant circle, right? Like, that's the computation. It's just one line completely, right? So, or triangle, 3 lines, like, and it's just a triangle in topological space, like a defect, and it just has influence. So that's like the way you can do things with this that I think has utility, because it lets you start to connect up the dots. And you have to sort of take some humility and say, okay, because there are more rules operating in physical space, I can make more accurate predictions because I can discover more of them. But the rules in valuational space will vary for different observers based on their cognitive light cones. Like, my experience of anger will not be the same as yours because you've got a different cognitive light cone to me. Or we might have partial overlap, but not the n many states of anger you can have. There'll only be like a partial Venn diagram with me. And as you go up to language, well, if you speak a different language to me, then you're going to have some mapping to my state space. But there are words in German that don't have direct analogues in English. This is another example of sort of partial overlaps. And then this sort of maximal space with long-range entanglements where you can't avoid but have sort of maximal overlap because they drive everything below it. So that lets you do things like...
When you say long-range entanglements, in this sense, do you mean like bridging a large distance on this hypergraph sense?
Yeah, correct. So like, imagine the computation at point... you've got two lines of computation 1 and computation 2. Computation 2 goes 2A, 2B, 2C, 2D, 2D, and then that gets to computation 2Z. And this one just goes from 1 with no intermediate hops to Z, right? It goes from A to Z in one hop, right? One line, as opposed to lots of dotted lines. That's the way I visualize it. So yeah, hopefully that gives you
no, totally, because it's like what is physically possible is like a subset of like what we can imagine, right? Like, I can imagine things that are physically not possible, but there's some kind of interesting interface between, I always say, like, between psychology and physics, there's kind of like economics, and so we can, at least in like an empiricist sense, like figure out what kind of economies work according to the laws of physics and the laws of psychology, and then you can see how
so this is the thing, like, I think this says something about that already. It says we value things that reduce the computational burden of observers. We value pockets of computational reducibility. We value things that speed us up, that give us more power, that gives us,
yes.
Money is just the proxy for that. We value things that give us more persistence in time. And because our relevance component depends on our causal history, we disagree and fight about it.
Right.
Most of the time. Right. That's the kind of... So you can make from these very two minimal things that define what an observer is, you can make claims like that is what value is. That is, for every observer, not just a human, like, that is value. And that is why this is interesting for me. I'm coming at it philosophically as unsatisfied with deconstructivist postmodernism as the sort of driving framework of our world, because it's clearly not working. We are witnessing it fail in real time. And, we're still suffering through terrible postmodernist thinkers in media who have kind of got that filtered worldview.
Right.
And like, no, we obviously need a better model, because if your model was right, it would work and we would be flourishing more than we are, instead of flourishing in pockets and absolutely dying in other pockets. Like, this is subpar now. Like, we need a better one. And so this is kind of the philosophical drive of why I'm trying to figure out a convergent model for observers, because if we're all doing the same stuff and we kind of have a proxy for what we maximize for, then the argument becomes how as opposed to what. right? And you just have to list the subs and list the hierarchy. And hierarchy here is the most real thing ever. There is a good and bad. There is better or worse, and the better or worse is measured against these metrics. And that is, you can, I'm not pretending for a second to have a view on what that better or worse is, because there are lots of people have lots of different views, but you have to have a common playbook or a common language to even talk about them without witnessing what we've, I used to want to live in America very badly when I was younger, when I was in my 20s. And today, I don't know if I would take that trade, even though London is terrible right now. So that gives you a sense as to even that gives you a sense as to why the why of this, the why of this from that was.
I want to make two connections there you just kind of brought up for me. Like one, it's like kind of where this goes maybe is kind of like what Leibniz and Spinoza were actually after, which is like, but they were approaching this like, can you have a geometric proof of like moral truths or something like that? Because they wanted to get there, right? But they didn't maybe have all the framework. But here it's kind of like, maybe we could get to the point where you could see like, from the perspective of like, sort of just computation and the constraints and like, in a society, like we need food, we need whatever.
You got it. It's in this presentation. We've got like the sort of toy model version. Like this needs development, and like there's the longer paper deals with ethics, but like you have to build the layers, right? So we're building layers right now. We've just done physics, so we've just kind of looked at how an observer-centric view impacts physics. Now we're going to move to like biology and chemistry and evolution, and then we're going to move to human things, right? So to make this code, when you're trying to do convergence, you have to be able to talk about lots of things and to make a convergent model or a model that can be applicable broadly. And so I have to build a foundation that links this to physics. Then I have to say how it links to biology under the same framework, then to directionality and telos, because I think that's, it's obviously if there's a point where things complete and you work backwards, well, that's an absorbing state. So I'm going to keep that. And then I'm going to move to humans and ethics and how that impacts our decision making as high complexity observers. And then you can look at how religions have dealt with that as sort of proxies or coarse grained models of that without computational language, and you can compare and contrast. Anyway, I'll take you through this. So I think the first point here is that evolution in observer theory is predominantly an informational phenomenon. It is powerful because we're surfing a pre-existing informational landscape with gradients, with sort of attractor basins and sinks. And this is not a new idea, right? Richard Dawkins, in his book in 1970 something, invented the word mean, and then just kind of was like, no, it's not important though. Didn't formalize it, didn't do very much with it. And then Susan Blackmore in 2000, who's this like incredible academic in Glasgow, published a much longer piece of work on memetics and memes that didn't sort of have the computational language yet, but essentially this is that sort of theory. And this is building now a computational model for evolution. And why it's important if evolution is informational, then ideas are evolving too. Like ideas are evolving too. They have selection criteria, they have fitness. And so this is just to sort of state that. So standard story, natural selection is complexity via variation, inheritance, survival. But there is no free lunch. And if you work out the probability of getting to us, it is outside of the amount of time and update steps in not just our universe, but I think in a few universes worth of our time, right? It's like a very, very, very low probability. Now, this isn't to say that like I'm one of the sort of, I'm not a theist that's saying, oh, evolution is obviously fake. No, I think it's real, but I think they've got the landscape wrong. It's operating on a sort of informationally structured landscape with attractors that maximize information. So observers, once they discover a rule, and Stephen's even done this, right? He's looked at 1D cellular automata. He's evolved them through time with a mutation, with mutational algorithms, and the sort of way they grow and get fitter, i.e. how they survive for longer as these 1D cellular automata, these patterns, they go flatline, 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 or jagged flatline as they kind of pick and choose rules. And then they'll discover a novel rule that will give them much more much more persistence in time, and they jump up exponentialization, jagged, exponentialization again. Like, so this is, again, actual, okay, it's computationally empirical, but it's empirical showing that there is some structure to rule discovery. And I think here, making that, it's the fine-tuned physics, it's chemistry, it's boundary conditions that we see in all scientific theories that enable this informational layer to work. And, you know, looking at it from an evidentiary perspective, it's physical constants appear just right. Now, fine-tuning in materialism has something like, I think, 26 brute physical constants and like 2 to 5 brute metaphysical facts, right? So it gives you, you know, for all the things that sort of physicalism says, there's still a load you take for granted. And really, this comes back to what observer theory is arguing about observer telos. It's saying that observers have finite bounded computation capacity, therefore their goal is to find the most reducibility, and therefore they're going to output the most computationally efficient region of this Ruliad, of this possibility space that contains the most attractor structures to let observers do this the fastest. And you've seen, you just said Leibniz and Spinoza, you can see the influence in the paper. This is exactly that, best of all possible worlds. And this is not just in fine tuning. In biology, it comes up in convergent evolution. And this is a very, very detailed and studied part of biology. In the sort of longer form paper from November, it's referenced ad infinitum, but it's like echolocation. And these are specific parts of computational possibility space that are rich with very strong attractors, right?
Yeah. Just to reframe, just because this is awesome. So it's I would say it's like similar, like human actors don't just like randomly try all possible business models, right? Like they intelligently think about what is my opportunity landscape and what makes sense. I'll copy things from over there. Similarly, you're saying it's like biological structures, say like cells and so forth. They also have a greater degree of goal directedness than you'd expect from random chance, and kind of what kinds of morphologies they explore next and that kind of stuff.
I mean, this is literally what Michael Levin's lab are doing, right? You can look at empirical experiments of stuff without brains, like sorting algorithms, fixing themselves or finding fitness. Like this is not this all look, and it's still early because undoing, you know, that Dawkins postmodernist everything's related, and is going to take a bit of time.
Yeah.
You know, he might need to die, but like he's like, the contribution's amazing, but it's now being empirically shown to be wrong.
Right.
Like, and okay, I don't know if it's enough yet to, you know, go, no, telos is in stuff. Like maybe it's not, it's just, it's in stuff. Sorry. Like it just is, but it's not quite there yet. But the empirical direction suggests that that's the way it's going. And that is, I think, one of the really interesting things, because telos and teleology and this idea of sort of active information has been out of sciences for a long time. You know, it's not been around for maybe 100 years, but maybe less. Like, information less so, telos more so. But the interpretation.
Like, also, just like if you had, say, like even in like a petri dish of reacting molecules that say are not bound cellular membranes or whatever reaction pathway has the most favorable kinetics will come to dominate that landscape of energy, right? Like if there's some cheaper way of getting to this thing, and that thing that it gets can replicate more of itself.
Path of least action applied all the way up.
Totally.
Yeah, like it. Yeah. And just for your benefit, the longer form paper, which deals with all of these big topics that are not in the formal model in the sort of 47-page paper you read, there's a section on chemistry and a section on their observation mechanisms and so on and so forth. You'll enjoy it. But the point here is interpretation, right? We're not a blind watchmaker, sorry. We're constrained search, right? Physical law, chemical spaces, environmental information, all a subset of the architecture of computational possibility space. And the implication is that, you know, survival and reproduction are really, really, really important for computational persistence. But because the deeper goal is to integrate information, because we have that absorbing state of maximal information at the end of this structure, that's where it ends, just has to end there. the deeper goal is to integrate more information, and that the boundedness condition becomes more important over time. So once you've got enough persistence in time to maximally explore a min-max of that, right? So we're not one of those creatures under the sea that live for hundreds of years, but they can't do very much. We found some min-max that lets us have maximal exploration with some form of exploitation that we can change. And that boundedness condition becomes more important in driving what we do. And in fact, are humans still physically evolving, or are we informationally evolving is the question, right? Like, it's not been very long, but it seems like evolution is operating in a new sort of frame now, in sort of mimetic frame that's moving much, much faster than the generational updates that we get every 15 to 20 years. So ignore the typos at the bottom. They are not all mined. The bottom, those 3 columns, that's meant to be deleted. That's a typo, but just to think about scales here, because we've just said that. So think about the scale, observer scales. How much of a possibility space can a given observer sample and integrate information about, right? Like, so that's to think about that R0, like that observable Ruliad for each class or each category of observer. So we have atoms, molecules. We get more molecules, we get combinatorial explosion. With life, we get self-replication with heritability, variation, which enables that internal loop to become more complex, that internal model. And then you have mind, and then you have network complexity for integrated overall experience. So what we do and what we feel, and also maybe animals as well. And then you have culture, and which is even bigger, right? And it's complex information across generations, right? And so just to look at types of observation mechanic, right? So, we talked about the atom. Let's talk about a molecule. So we've got conformal scanning, we've got spectroscopy, we've got bonding, we've got reactivity and catalyzation, and then we've got life, we've got chemotaxis, chemical gradients, right? Fitness landscape, quorum sensing, gap junctions, and then you go up to mind, and we hive off neurons as specialized information integration apparatus that a plant doesn't have, because it must be valuable. Why is it valuable? Not just survival, because we need to do this second part. Network topology, we can figure out the path length. We have some natural predictivity about what we can see and do. And plasticity, we can change our internal function, right? We can change our internal model. If we focus on something long enough, you go and play piano every day for 12 hours. In a few months' time or a year's time, depending on how quick a learner you are, you will be a piano player, and that is brain plasticity. So we can change things much more than anything else. We have much more agency. And agency here, and you saw this in sort of the paper, but talks about morphism selection. You want to maximize your possible choices as an observer. You're trying to have the most possible set, the biggest possible set of choices to explore between hypergraph updates, the biggest possible set of morphisms that you can sample, computations. So this page deals with observers like us, and deals with how we group and how we do that thing that builds culture, that builds that bigger meta observer than just an individual human. And these all experience that same sort of exponentialization. That this is a drawing, so please don't take this as proxy for what the actual curves are, because this is still theoretical. But the structure is self-similar to what the different categories of observers can observe. Each transition in coupling technology, which is how we communicate, exhibits jumps in network capacity, new capabilities, reorganization of our social structures, and acceleration of our innovation rate. So start with language, it's the slowest. We get to 150 individuals that can live in the tribe. We get to writing, we get the first kind of cities, right? Small cities like 10,000, tens of thousands of people. We get to printing press, we're suddenly in groups of millions. We get to the internet, we're in global range, and now we get to AI, and we're at this new step where, what does it look like? Like, we're still figuring what this looks like now. But this, you can see the time between jumps gets less and less, which was what you would expect if you had sort of this going best of all possible worlds way. You would expect that acceleration. Again, these curves reflect or correspond to what Stevens found in 1D cellular automata, which, if they can be counted as observers, which this formalism says they can be, then you would expect it to have the same type of shape. And this is, I think, what we see in terms of what we see in history, right? This isn't, I know this this sort of diagram, this graph is drawn badly, but it is the same structure. It is self-similar. It is a different.
It's a good diagram, and it makes me. I mean, it's awesome because it's kind of like we started from the beginning was like constructing larger observers kind of depends on like this like bandwidth available for information processing, right?
Correct. And
then it kind of gives us kind of a better, more grounded way of approaching this concept of like super intelligence, where it's like you think this is going to be like a single mind, but like actually like civilization is kind of a super intelligence because it's like solving
problems. Yeah, because you get more. So that's exactly right. You get so there's a theory in network theory called small world networks. Yeah. So once you get to sort of networks are joined up enough, they get emergent dynamics or parallelization of the computational burden, which means they can do much more than the individuals or that disjoint network that might not be as coupled. So these networks have utility. Why do our cities get bigger and bigger? Why do this is why? Because we want more computational capacity. Now, whether or not you think we're just computing or not, it seems like that's the way to explain what we're doing. And that's the point, right? Again, I come back to the criticisms I've had that, you know, consciousness can't just be computational. I'm not saying it is. I'm just saying it's the best way to model and explain it. And I think this is another sort of feather in the bow of how to think, why this theory is useful, right? I don't want to write a theory because, you know, I've got a theory of it. It's not, you know, it's like not a theory of everything to, you know, here's a bunch of invented terms and a bunch of axioms that aren't that like you have to take. It's like, here's a very famous scientist who might be controversial, but has published a lot. His research has published a lot. It's peer reviewed. This structure outputs physics. Can I apply this structure to something more? And this is the top-down version of his model. This is like the philosophical version of the Ruliad as opposed to like the physics version. But it's useful because you can actually make the philosophy touch physics, which, believe me, most philosophers get nowhere near. And so that's why I think it's kind of neat and tidy and quite interesting. So now just moving quickly through telos. So observational complexity to universal telos. So this is the information integration thing for all observers. So the threads, physics, symmetry breaking, Planck limits, structure bounded observable universe, that observable Ruliad, evolution, writing pre-existing gradients, observers with complexity and phase transitions that track how deeply observers can probe our reality, our universe, based on their networks, based on what they have access to. And this is like the story, right? We are trying to get more structured information at all possible scales, or to recover structure from this computationally irreducible reality, this sort of infinite ground. And observers are the mechanisms that make this happen. And it's one gradient. It's like one deep attractor at the end, this sort of infinitely informationally dense endpoint. And that's like a gravitational pull analogy, not actual gravity. Might be like something like mimetic gravity that pulls all observers towards it. And this is like the conjecture in the theory, or the claim that this is what observer theory implies in this type of structure. And the nice thing about it is we can now go, what is universal telos? How we formalize gradients and sort of informational hierarchies, or how dense or how detailed information can be, and what different types of information there are. And how do we connect this to things like consciousness, meaning, and ethics? Meaning, this is kind of cool. So a couple of, you know, a little primer that you will probably be very familiar with is complexity measures, how far an observer must travel, or how far the computational chain must travel to reach a piece of information. So O1 directly from your state, ON, N hypergraph updates away. As we said, the hypergraph updates faster than our experiential time. ON squared, you need to explore a region of the hypergraph of your computation. O to the N, multi-way explosion, it's somewhere in like the branchial graph. And in O infinity, i.e. the point at the end, you can't get there, but you know it's there because it's a closed structure. And then oh yeah, it's like, look, I wrote, you know, because there's a lot in the long paper is like 300 pages, right? It's like it's a big document. And so the long paper, to break it down I'm writing at the moment, like I'm not so great at translating, but I'm writing like Substack posts about, you know, how this applies to many different ideas, right? And so one of the things that I reference in there is Teilhard de Chardin, that omega point. You know, this is a Christian metaphysician, you know, and it's that sort of idea at the very end, right? Like this absorbing state. And then Ruliad framing, we've got hypergraph with state and rules, and the complexity measures the length and structure of the morphism chains you must traverse or compute over to find your desired state. And then the question is, given your limited resources, what path should you invest in? Where should you go? Which strategies minimize cost per bit of useful information gained? Now, again, this just comes all the way back to surprisal and FEP that we talked about at the beginning. They have a probability measure. I'm trying to give a deterministic measure for the same type of thing. So this is saying something like that is probably close to right, but the measure is not huge. I don't know if the measure in the current form of variational free energy is integratable with science in the way that like a bit measure because of Lauder's principle is. Like that's the point. You can convert bits to energy. Like that is a real thing. I don't think you can convert probabilities to energy. At least I'm not smart enough to. But that gives you a sense as to why I think this is useful for something like FEP as a formalization. And then information gradient. So you'll recall that we just said this point at infinity has infinite informational density because every computation completes there. Therefore, it has all of the information from all of those computations. Now we work down. So what are the most causally influential things that we have? So we say what we've done is look at our cognitive. In the paper, I look at sort of anthropomorphically what domains observers like us sample. If you wanted to split these domains differently for a different type of observer, you could, right? As long as you have the sort of physical thing at the bottom. And my claim is you probably need like the M domain, this domain of pure geometry or logic, like the most basic structures that enable you to comport sentences to make a computation. You probably need those two. What you stick in the middle, researcher pick your poison. If you want to take that physical domain, split it up into 10, 20 others, well, that's what an infinite group is for. You can do it. You can just do that. That's fine. So here I'm just giving us the bigger buckets, right? So working top down, we have the point at the end, which is infinitely informationally dense. Then you have what I call the minimally constrained domain. These are like Jungian archetypes, like big patterns that apply to everybody, mother, father, etc. Geometry, logic, like and, or, not, like you need them. And then you have the S domain, symbolic domain, which can be language, culture, mathematics, as in formula descriptions of mathematics. You have valuational domain, anthropomorphically that's emotions, but that could also apply to, animals who don't have emotions. It's like building maps. And then you have the physical domain, and you have more rules in P than you do in M for a stable object. Think about it in terms of you. There are millions of rules running that let you hold yourself in your body at all scales. But there are very few rules that I need to construct a triangle. Like that's the sort of way to think about it. So more rules means less informationally dense. I have more jumps, right? So the object's smaller. The objects are smaller versus bigger.
More rules. It's like more structure, encoder, decoder, or something. It's like you have more interpretive, and it's kind of like if you and I both have the same cultural context, I can convey a lot of information with just a few words by making reference to some South Park episode or something silly like this. Like
correct, which is why it lives in like the more dense. It's more dense than like physical. Yeah. And so I've tried to shade at the bottom like a sense as to human, animal, and atom, right? Like, so they're all on one scale. It's all on one continuum, but the continuum is not linear. It is like a stepped sigmoid, right? Like it's like a multivariate. It's like a sigmoid that goes up and up and up and up and up, and it gets shorter and shorter because this should move as fast as it can. Okay, so just to break that out into a bit more detail, just to give you this in a bit more language. Informational hierarchies, we have constraints going down. constraint is lowest at the top, highest at the bottom, and abstraction goes up, right? So more abstract concepts live higher up because they have more causal coverage. They apply to more things. Direct observables, maybe O1 access or ON access. It's sense data, the particles, the fields you were talking about. Inferable patterns, which is a more general form of saying valuational, is motions, preferences, goals. Computable structures, language, theories, law, myth. Intuitable archetypes, universal symbols, logic, archetypes. And then this sort of point at the end, which is where you kind of get to be able to start talking about theology within the context of observer theory, because computationally this is a coarse analog to what mystics describe as ineffable reality, or the infinite, or I saw God. Like that is that domain. That is a domain. They're saying they got to the boundary. They're saying I'm at the point. I'm there. And so the properties are the higher domains contain and constrain lower ones. Categorically, a pre-image of the lower domains exists in the higher domains. It's a nested, joined up hierarchy, right? So these all compose, and they all compose together. The observers move integrated information upward from raw data to value-laden meaning to abstract insight with loads of causal coverage. And then taking it back to the last point on theology, ancient traditions, or anyone that survived, right? So the monotheisms, Hinduism, Taoism, Buddhism, which are the ones that sort of stuck around, they intuited it. They function as the limit setting devices for that observable possibility space. And you see different constructions of this hierarchy in different languages of those traditions, but with the same overall structure, despite having limited or very little cultural contact when they were being formed. So it's the Kabbalah in Judaism is the four worlds, and that applies also to Christianity and Islam with slightly different wording. Hindus, koshas, Platonic forms, Osmatus and Nous, can't remember the Arche and the sort of Platonic one, the Platonic chain, and then you also have Taoism, which is like the Tao, the 1 to 2 to 10,000 things. It's the same structure all across the world. So how are humans coming up with exactly the same structure despite not touching or not meeting?
Let me riff on this for a second, because this is a very interesting talk. So this information integrating and processing is kind of a bottoms-up process. But this aspect of Talos is kind of a top-down thing. And I think I mentioned this earlier, where it's like we as large classical scale observers can influence the outcome of measurements of small systems by our choice of basis of measurement in some way. And if that top-down perspective occurs at, say, biological organism to molecular pathway chain, then it kind of can help understand, like, how could molecules have a goal-directedness in some way? How could they explore the configuration space more efficiently? And that's like at our level, like, we have the curse of dimensionality for exploring like social space, right? Where it's like,
yeah.
And there's like these interpretive degrees of freedom where it's like an event happens on the news media, and like depending on my framework, like I can interpret this different ways. But there's some kind of source of truth that is maybe above our level of direct awareness that is filtered down.
So this is what philosophy and religion do, right? Like philosophy and religion inform that top down. Now, if you're an atheist and it's philosophy and you're like, I believe in, Wittgenstein or Deleuze, and I think that, because postmodernism is a gigantic space, right? Like, just to be clear, like I moan about it, but postmodernism is an exceptionally effective search algorithm, because it basically says and you can compose any causal chain from you as long as you believe it's truthful and valid, right? Like that's that's basically deconstructivist relativism or postmodernism. Like that's what it says, right? And what is that space? Well, it's the space of nothing, right? And so the idea of nothing is a very big fucking space. And so it's exceptionally efficient to search the space very quickly. But at the limit, at the very end of it, it doesn't have a convergence to it, which is in the structure. Therefore, it's inefficient at the limit. So it's short-term efficient, like maximally efficient, long-term inefficient. Divergent versus convergent infinity, right? Like that's the basics of it. Like, and so when I dig it out, like postmodernism gave us loads of stuff. It gave us like music, dancing, everything. It gave us music, art, culture. We got to like the best part of it, probably at Obama, and then it's been sort of a slow downhill, a slow to aggressive downhill trend since. But like, it's not, it's not like it. It's not to say that like these top-down dynamics, right? All I'm giving is an architecture of how it fits together here. But you could do what you did and go, oh well, if I'm setting up a measurement device and I'm doing that teleological pull or some very minute version of it to this structure, I'm directing it, I'm pointing it in this possibility space to be in this set of states only. Like it can only get to those set of states because of how I've set it up. And so that's that's like the analogy or the connection. And again, the self-similarity of this structure, because it's nested and embedded, that should be what you observe. Again, it's like it should fit. Mm-hmm. So the core conjecture of the paper you read, all observers share the same telos, which is maximize integrated information subject to your boundedness and persistence. And the intuition here is that observers that integrate more useful information or find more structure and get more predictability survive longer and spawn more observers. So it's recursive, but upwardly recursive. It builds on itself. Survival and reproduction are instrumental, but as I said, information structure integration is deeper optimization. But you find it in biology, in culture, and in spirituality. And so, the bottom part, can we define meaning computably? Can we say, like, what is meaning? Is it the integral, the area under this graph of how much is encoded, how much it matters to the internal model, and the temporal persistence? And so what's really, really, really interesting is this was written, this paper was, I gave this presentation at the end of December to the Platonic Symposium. And a few days ago, OpenAI's researchers came out with a paper where they implemented a new measure for complexity called epistemic complexity, which is like the corollary to entropy within a large language model. Mm-hmm. And it is literally, this sort of, it's this sort of structure. It's the formalization of that sort of idea, and it works. And so that's pretty interesting here for, how you look for how you start to compute, structure for finite and bounded observers, which is something you couldn't do with Kolmogorov complexity or Shannon information because of the nature of the assumptions at the top end of it. So again, we've talked about this, so I'll skip this because I'll skip this except for one point, and this is that we're starting to see empirical support for this top-down telos. I think the observer theory perspective is that systems that don't integrate information die out to entropy. They lose their boundary. And systems that do become more complex, they build bigger boundaries and have more causal influence. And this is consistent with Darwinian selection and the observed acceleration of complexity. So it doesn't say complexity is random emergence. It says it's structured, and that's, again, a different prediction. So efficient search. Observers at every scale evolve optimal strategies for exploring this space given their constraints, and they get more sophisticated, balancing exploration and exploitation. And here we talk about how we map those to the complexity classes. So with Brownian motion, gas in a box, gradient following, bacteria, memory-based search, animals to us, symbolic reasoning, us, quantum search, quantum computers, or the theoretical limit. And then what you get in religion, which is the idea of prophecy, which is this direct knowing, right? Like yes. That's in what you get in deep meditation, what meditators say, right? So it's not just religious people, right? You can talk about someone who's done transcendental meditation who's not religious for 30 years, and they'll approximate something like that. So informational efficiency. Why is efficient search better? It's better because observers that can pay the upfront cost, because more complex search requires more energy, they gain huge long-term advantages. In fact, they gain exponential advantages in integrating information, and therefore selection is favoring architectures implementing those efficient strategies. And then you again map it to the sort of categories I gave you on the first page of this section. And then you say, well, this trajectory seems universal, and therefore survival must be derivative It's only required so that you can continue to integrate information or continue to find structure. So this is now moving on to ideas now. So ideas as abstract objects, how do ideas in this structure, like computational ideas, ingress into physical reality? And here we're looking at ideas as superstructure. They ride on top of sufficiently complex observers, and they're like a phase transition, an exponentialization in how information is organized and integrated by observers like us. And the question is, what roles do ideas play in shaping our experience reality? So ideas here are persistent information patterns or persistent patterns or bundles of computations in the Ruliad, and they can achieve autonomous existence in structure like attractor basins that grow based on the observers looking at them. They get more equivalences, right? So if an observer computes over an idea and they stay computing over that idea, they find more equivalences, more things that are like the idea, and therefore that sort of attractor, that basin in this Rulial space, or this, non-trivial geometry that's being outputted, becomes more clear, becomes more obvious, but has more like mimetic weight is the analogy I would use, right? It's like pulling observers towards it. And they're not the same as genes. Ideas can jump across species, substrates, and across cultures, so they're much faster. And you get a new landscape for evolution. So you get a faster fitness landscape. And it's no longer just the organisms, the physical substrate in the P domain that's moving up to increase persistence. It's ideas evolving within and between observers and classes of observers. And that moves much, much, much faster to the point now where ideas can spread in seconds, right? And this is a point, I write about this in one of the substacks, about the maximization function we're running at the moment for ideas is attention-based and not truth-based, or not value-based at the very minimum.
Yes.
And that is probably not a good thing in the medium term, because certain classes of ideas are very easy to gain attention for, but they're not very useful because they appeal to a low down part of the domain. So, why is porn valuable? Because porn is something that everyone knows they need, like it's a proxy for persistence, right? In the physical domain, it's like a low informational object. So we shouldn't be optimizing for that. Even if you find it great, it's not the thing.
Mathematical argument against AI slop, which I love, which is great. It
is 100%. It's 100% a mathematical argument against AI slop, or a logical argument. I think I'm giving myself too much credit to say mathematical, but certainly a logical one. So the formal structure of an idea. So you can design a tuple for an idea, and here this is sort of an attempt that builds on some of the work from Susan Blackmore, again formalizing it computationally. It says here an idea is built from the pattern, the replication rules, its fitness function, its mutation rate. And so those component parts are pattern, which is the structure of the idea, or the sort of structure of that geometric object, or that basin in that sort of attractor in computational possibility space. The replication rules, how it spreads and sticks for observers like us, because we're the relevant party for most ideas. So valuational domain, it might be the emotional resonance, it might be in the symbolic domain, or the minimally constrained domain. The cognitive fit in the physical domain, it's utility for us. And in all domains, the coherence, does it conform to your causal graph, to your cognitive light cone? Can you easily compute it from where you are now? So let's pick an example. If you're Donald Trump and you say, you should just do all of what Bernie Sanders is saying, that won't conform to his causal graph. Therefore, the computational power that he would need, or the computational cost of engaging with that idea and integrating it, is too high within the time he can loop it around. So therefore he won't do it. It doesn't compute, right? It literally is like, this doesn't compute is that in action. And so
this reminds me of a lot of stuff where it's like the degree of rationalization to hold on to some preferred narrative becomes more and more complicated the more it fails to encounter reality. Like you get all these
because you get more equivalences, because you make more equivalences. So by focusing on that idea, you build more internal structure for that idea within like computational possibility space. That structure that you're building is like more connections that make this object. So you're like embedding this object. And so that if you're going around in a loop, like a recursive loop down, because you're only looking at one idea, well, those things are going to get more and more tight within the object. They're not making the object bigger anymore. Do you get the point? They're like filling in the gaps.
Yes.
So fitness function, how effectively this idea replicates, and virality here is proportional to the causal influence of an idea, top down and bottom up. I haven't specified it yet because this is still early, over its computational cost. And then mutation rate, how much does the idea change with each transmission? Just like the mutation of genes, right? So this is how you formalize an idea in computational possibility space, at least in my view. And then for us, ideas are structured as objects in the symbolic domain, right? Because we express our ideas with words or with symbols. And the special features of an idea versus a gene are they include their own replication rules. And so when you get an idea, what does it spawn? If it's in the S domain, it spawns morphisms, or it gives you access to morphisms in the valuational domain, which you have like a good idea that you love. You might be able to feel happy now because you figured out philosophy or whatever you find interesting. And then you get a new physical behavior on the back of an idea that's integrated. And this is a new evolutionary arena where ideas compete just for attention and memory, right? They don't compete for persistence in the classical physical sense, so they don't survive physically, right? But they survive as long as they're within our boundedness. We're using computation to observe them, and so they form stable attractors. And this is analogous to biological niches within evolution, within physical evolution. So ideas shape reality, and the claim is that these ideas are not epiphenomenal. They shape what becomes real in less informationally dense domains. And the example mechanisms as listed: physical embodiment like the placebo effect, beliefs change brain states, change hormones, change behavior; epigenetics, chronic stress altering which genes turn on and off; meditation is the sort of good version of that, because if you meditate a lot, you find that you might get healthier, your skin might be better. These are all qualitative and sometimes quantitative reports about, down regulation of your DMN if you're a meditator, right? So your DMN in long-term meditators is not permanently, but is down-regulated compared to the average person. Again, this is empirically shown. Social organization, shared ideas create norms, laws, and institutions. So fiat money is an S-domain structure, but it moves trillions of P-domain dollars.
Remind again, what is S-domain?
Symbolic. So like anything symbolic. So like anything constructed with words, like, numerals, like letters, anything like that. Mm-hmm. So these structures constrain which morphism choices observers like us have in the valuational domain, i.e. the emotional domain anthropomorphically, or the physical domain. So, and like the classic line is, you can't build a rocket without the physics of rocketry. You need the sort of S domain idea before you can get those structures in those less informationally dense domains. And the feedback loop. So this loop kind of looks like the loop from before, but it's slightly different. Ideas shape reality, reality shapes ideas. I think the easiest example is to look at the example. It's the idea of heavier than air flight is possible, the prototype, your observation, it flies or crashes. You update theory and design, and you repeat until you get a big plane, like you get a jumbo jet. And each loop here, this observation loop of the idea, like specifically to these symbolic domain ideas, they deepen the idea's computational persistence with more equivalences and embeddings. You're discovering more of the structure in this possibility space, and it's permanent. Once you discover the structure, because information is always increasing under an observer sampling, and there's a sort of proof sketch in the paper you saw about that, you can say that these things are building themselves in possibility cells, being discovered, right? So nothing is invented by us in the Ruliad. The Ruliad is there. It contains all these structures. So everything here is discovered. I'm not just like math is discovered or invented. I'm saying everything is discovered, not invented. And that is a function of us as observers. And then the last point, paradigm shifts therefore cost massive energy, massive computational cost, because you overwrite a whole class of efficient models, right? So that's why paradigm shifts normally come with violence or, social upheaval, because you are really, you're basically saying everyone point here and now point there, and it's very far away. So what are the selection pressures for ideas? Mimetic selection pressure, explanatory power, emotional resonance, social utility, practical utility, and simplicity. I won't go through all of the examples because it'll take too long, but the claims here for each one are explanatory power, ideas that compress regularities, i.e. more predictive, are more useful. emotional resonance, ideas that activate your emotions are more memorable as they touch more points in your cognitive light cone. They are easier to integrate. Like ideas that solve coordination problems spread widely because of the network stuff we talked about. Practical utility, ideas with repeatable benefits gain wide adoption because they are easy to use again and again and again. They have low cost after the first time. So the cost goes very high and then drops off a cliff. Simplicity, simple ideas spread faster, but they are subject to more distributed interpretations, right? So simple idea, like imagine like, you know, the meme of the guy turning around with the girlfriend that's put with a million different things.
Yeah.
That is like the idea of a simple idea, but the interpretation of what it's talking about or what it can be applied to is so broad. It's kind of like that idea.
Yeah. Yeah.
So again, you can apply the computational cost of these ideas and look at it in terms of that complexity chain. And look, I've bucketed these into what I would call, big categories, and other researchers in memetics who are much more studied on memetics than me may have a breakdown that's more accurate or more detailed. I think this is really just to give a sort of heuristic for how to think about it so that you can, if you're a researcher in memetics, you can apply this to the very detailed set of things you think are important. But it basically says different complexity has different transmission and different transmission speeds and different persistences in time. So simple ideas, utility is fast coordination, fire, run, right? Complicated idea, like a skill or a recipe, transmission might be slower, persistence might fade without practice, but it's practical, it's useful. Complex ideas, dense web of interlocking ideas across all of their domains, takes years, cost is huge, but you get growth of your field of observation and potentially your observable Ruliad as a result of a complex idea. And then chaotic ideas, these are radically interconnected and reframe or restructure the rest of the domains irrespective of the ideas that already live there. And those things are very rare, but what are they useful for? Effectively growing your total observable Ruliad. They escape, like pre-QM, right? We've solved physics. Like physics is done. I think there were like very famous scientists that says, oh, there's nothing to do anymore. Got GR, it's good. Yep. And then you go down and then you get QM and the whole thing pivots on itself, and every single thing downstream of it has to change or has to be adapted for, right? That is an example of, and that also grew our accessible possibility space dramatically, right? We were like working, with these electrons, we didn't really know what they did. And now we're like, oh God, we can go all the way down to this like Planck scale. Like that's like a huge, was it 10 to the minus 10? 10 to the minus, 20 orders of magnitude away, 25 orders of magnitude away, something like that. So that gives you a sense as to how much it grew our accessible state space. And then here, this is a bit more, this is a construction that basically says it's the area under the graph thing from the prior page, right? It's just stating that in sort of an integral formula, and it's not accurate because it's a discrete model, but instead of showing like, a discrete summation, which is quite a complicated formula to write, I've been lazy and put the integral. So sorry to people who are going to get, sorry to people who are going to get upset about the sort of loss.
How do we know those converges? I always hated those guys in class that would say those things.
Well, like in the paper, it is done as a discrete sum. So it is done right in the long form paper, but it was very, very hard to put it all on one page. But the plain English here is how do these ideas interact with our view of meaning? What we want to see is structure, how much it matters to our boundedness and persistence goal, and whether it endures the idea. Does it last? And high meaning is lots of this info that's highly relevant, that's long-lived. And zero meaning is high info, but no structure or relevance, right? Pure noise, right? And so the reason I'm so excited about this new paper on epistemic complexity is it basically gives a computable way of figuring this out, which is probably not what they're applying it to, because they're applying it to like LLMs and sort of, finding interpretability in an LLM. I'm more interested in like, forget the boundary of the LLM for a second. If I just spread out this computational network or this sort of multi-dimensional structure, can I use this to kind of proxy this number? And that would be quite cool. Like this idea means X. So that would be fun. And then last but not least, computational ethics. So we've got all the way through like physics, evolution, telos, ideas, and now how they meet with ethics. So reality for observers is only possible computationally, not is a computation, modelable computationally. Observers here are bounded samplers with a universal telos, and ideas and cultural systems form formal causation, top-down causation superstructures that shape what we can do. So the question comes up, if the universe is structured and telic, what does it imply about ethics? And the claim here is that, like everything else in this structure, morality isn't invented, it's discovered. And ethical behavior is mathematically optimal behavior, exploring the fastest information gradients or the deepest attractors for the most observers. Virtue and sin, therefore, are about information integration versus informational entropy, or about epistemic complexity, if you want to use the word from the new paper, versus informational entropy for self-referential observers, us. Ethics emerge when we ask which sequence of morphisms, which sequence of choices of which computational routes I take are good or bad. And so globally, entropy still increases, but locally we create negentropy, life, knowledge, society. And ethics is a study of what choices maximize integrated information per unit entropy, or the ratio of those two things. Which choices throw away information and accelerate disorder. You can't get rid of information totally, but it's a proxy or a metaphor. So choice is computational optimization. So this is defined more formally in the paper, but path cost function. For a path through the Ruliad, y from state 1 to state 2, the total cost is the number of steps, the number of jumps, plus the entropy times the weighting on the entropy generated, and the distance between that and the endpoint, and then the network effect of that. So it adds all those things up together and says, how many steps does it take? Is this getting me to the end faster or slower? And is it helping more people or more observers like me get to the end faster or slower? However, this doesn't just apply to observers like us. This could apply to any choice of any observer in the Ruliad, right? So this is can be abstracted down to like an animal or to something else, right? So it can be used all the way up and down. Again, the point of this idea or this theory is you apply it to all observers. It's just that what composes that part of the function or what goes into it is going to be much more complicated for us than for something else. And so
I've given a direct connection here where if you have this sort of information to energy equivalence, and then you also think of like the path of least energy, the path, like the action minimizing path for physical systems, like this is true for these things. Like the ball doesn't like roll uphill and then back down, this kind of stuff, right? In this sense. Yeah, and then also,
yeah, it's the same. It's the same. It's principle of least action applied to an endpoint, right? Because you need the telic endpoint, otherwise you don't know what the least action is towards here. If it's an open category, it just goes on forever, like a giant tree, right? On the right-hand side, I've given an intuition for sort of how you can look at this, from like helping a stranger to lying, to kind of get a sort of heuristic understanding or an intuitive understanding of this type of idea. I won't run through that in detail because I'm conscious we've been talking for quite a long time. So what is ethical behavior? Optimal
This
path
is the good
selection.
stuff. Here we go. Mathematics of good and evil. Yeah.
I like funky titles. What can I say? Like so that path one be the virtuous path, and y2 be a sinful path from your current state to the end state. And then if the cost of the first path is less than the first, and the integrated information is higher, and the entropy is lower, and it reaches convergence faster, then it is virtuous. Paths that maximize information integration and minimize entropy and speed up convergence. So it's reducing ethics to like pretty tractable ideas, right? Like I think, you can, look at meta-ethics, and meta-ethics does a lot of this, I think, in its formalism and its philosophical formalism without computational language and without sort of linking it to mathematics. I think it does link it to logic and analytic philosophy, but you can use this computationally to kind of get an idea of what's good or bad. And that's the idea that if you apply this theory, you can now say ethics are real, and there's a reason for these convergent ethical systems that's not just philosophical, it's computational, it's not social, it's not culture, it's not some guy went over here and told them about the rule of law. They are attractors. They are big attractors because they allow more observers to network, and that is always good, right? Small world networks, good. And this falls out again of the structure, the observer loop, and this again falls out of the priors and the primitives of this idea. With the primitives, you get this as a natural consequence of the primitives. You don't get it from adding a bunch of stuff. I have a path, I have a network, I can map how many steps I take, and that helps me determine, and I know that I'm trying to get to an endpoint. Therefore, I can map this in a way that, therefore, I can non-trivially say what ethics are in this structure. And then,
to say though, like pragmatically, you don't actually know what path is optimal ahead of time. Like
it's always a guess. It's computationally irreducible to know the perfect answer. So why do we fight about what is ethical and not ethical? Because our cognitive light cones don't overlap, and therefore we fight about it. And that's the consequence of imperfect prediction because of our computational boundedness. So because we cannot predict perfectly, therefore we don't agree, because from your perspective where you're pointing, we might not overlap. And therefore I go, no, this is the best way. And you go, no, that's the best way. And then we disagree because our maps don't compose.
Well, I guess more sort of what I was going to say is that this the exploration of some information wasting paths is like a necessary or an inevitable component of this, like searching for like the virtuous path. Like there is, you actually cannot not make mistakes, that the mistakes are the part of the learning that is necessary to find. And
this is what religions say.
Yeah.
Right. Why, like the question that atheists always ask theists in monotheism is like, if God's so fucking perfect, why did why did he put the tree in the garden?
Yeah.
Because you can't fully explore the space without seeing all of the regions of the space, right? So you are going to make bad choices. So this is like the bad choices are in the service of growth towards some goal, right? Like that's the computational answer, at least. So here now, like that, we sometimes do things that create disorder already, right? And like we just do these things. So I think here I've had to define something new. So this is called computational debt. And the idea is that computational debt, it comes from choices that appear optimal in the short term, i.e. within the bounds of your predictive model, but they require extensive additional computation to integrate coherently later. So every time you make a choice, because your model isn't perfectly predictive, just what we've said, you're going to incur some computational debt for that prediction error. And so you might make a choice that based on your causal graph, you think is optimal and good and right. And you may be wrong because, what you're covering or what you're looking at or the coverage of your causal graph is already in a suboptimal attractor base and it's just not in the optimal place. And even though you think it's right, well, if you ask a bad person, if you ask someone who's, if you ask anyone if they think they're a good person, you will find very rarely people say deep down they think they're a bad person. And this is kind of that playing out in computational language. Why do these people who are clearly, why do they make bad choices? They make bad choices because their internal model is suboptimal. And so here we look at debt as the actual cost of the choice versus the optimal choice. And now these are, I don't know if you can compute these, but it's a proxy definition to enable you to think about things like lying and things that have short-term negative consequences, or things that might cost you as one observer nothing. Right. They might be good for you in the short term, but globally they're bad. And
conventionally, it's like it's very easy to always tell the truth.
Yeah,
it's like
the intuition. It's not always easy to tell the truth, and in fact, this example will go for it. But the intuition here is that computational debt is like the ledger of extra computation needed to maintain a suboptimal pattern and then correct it later. I.e. the trade-off between computational reducibility now, because you've got a reduced model, and the additional complexity of entropy and lost chance of having to recalculate that model. And so here we've got lying as sort of a paradigmatic example of this, where it works short-term for you as an observer, but it's globally suboptimal for the structure. Green, good choice. Truth, high emotional cost now, right? So your computational cost emotionally for telling a hard truth might be like, I'm going to feel bad, and that has a cost. But at state greater than zero, or time greater than zero, it's got no cost because you've already done it, right? So you just have to work out, you're still working out that back-ended computation. But lie is low cost now, but it requires, after that step, extra modeling. Remember what you said, extra constraints. You can't do certain things because you've told that lie. Extra risk. If you have discovery, your network with that observer, the shared computational power above 1 + 1 = 2, like the synergistic effect of that network, goes away. And then you have extra energy expenditure. So you actually impact your persistence function. You have anxiety, you have to monitor. This is additional computational work that could have been spent on better things, learning, discovery, not lying. But that gives you a proxy for how to think about ethics with a computational hat on. And then just to bring it back to all of the ways that we pick ethical systems. So there is one optimization problem, which is what we've stated so far. And the convergence is major ethical systems approximate the same computational optima. And I've just given some examples from theology. So Buddhist eightfold path, minimize observer entropy. Christianity's love your neighbor, maximize observer network integration. The Noahide laws in Judaism, which is like the 7 laws that every human should follow, right? They're the minimal generating rule set, the categories of rules for every stable civilization, not just Jewish civilization. Islam's taqwa, align your personal will, your personal cognitive light cone with that optimization point, with the endpoint, i.e. do the thing that the endpoint says to do. And Taoist Wu-Wei and Dharma, maintain the cosmic order, follow low entropy paths, least resistance. And then the analogy in biology is eyes evolved independently because vision is useful. It has utility for survival. It captures the most information from the P domain, i.e. it's got the maximal input to your model. And those ethical systems converge because coordination and low entropy, low information entropy are always useful in observer networks and observer theory. They're always useful there. It's a universal. And so they're local approximations given bounded computational power of observers who are making these, making these sort of laws and rules about how to be ethical of universal optimization problems. So they're like roughly pointing at the attractor. They might not get it perfect, though they all probably say they do. But the fact that they exist means they're pointing in the right place because they've been persistent for thousands of years. And then these sketches, I won't run through these because this is a bit detailed, but you can basically try to start quantifying ethics with information theoretic measures. And again, I come back to this paper because the fact that they've come up with a finite measure for epistemic complexity versus entropy is so useful for starting to formalize these things. But these are, how do you apply these ideas to individuals, to organizations, to civilizations, to species, and what can you look at as evidence that this sort of dynamic is undergirding the system? And so we look at individuals, it's like good behavior correlates with your well-being or your sense of happiness. Again, there is evidence in this, but they're all sort of disparate pieces of evidence because they go across lots of different subjects. And this is really an interdisciplinary paper that's saying, how do we frame all of those things you're finding in a coherent narrative that makes sense with physics, with biology, chemistry? Like it's that sort of philosophical framing that's trying to do this here. I'm not going to go through this in great depth. I'll happily send you the slides if you want them, and they're also up on the Substack, on the GitHub on my profile under the God Conjecture, because I spend a lot of time talking about theological models in that, but it also has all these slides and the video presentation I gave to Wolfram Institute and Levin's Platonic Symposium, which walk through this for you. I guess the conclusion here is ethics are like an operating system for reality, and they are discovery of optimal trajectories for the function that we think observers are doing. They're structural, like maths. They're not preferences or social conventions, and postmodernism is wrong about ethics. Though meta-ethics is slightly different because it's constructivist postmodernism, and it's actually not far off. This is like a formalization of that. Virtue corresponds to minimal cost paths, sin, maximal cost paths. And so where does theology come into this picture, right? Because I talked about theology a few times here. The closure point of this Ruliad structure, this compactifying point infinity, shares certain properties that theists attribute to God, like necessity in the structure. It must exist, otherwise the structure doesn't work. Omnipotence, it has all the information from prior to it. And omniscience, it's the whole structure in the limit. And therefore, perfect justice in religion is optimal pattern arrangement, maximum integrated info with minimal entry, and perfect love in Christianity is maximal observer coupling. And they correspond to the limits of the observer's optimization function while being in the physical world, right? So there are ideas like that. And you can even use like a computer hardware, computer science style look through, and you can go, here's my hardware, it's the Ruliad, the kernel is physics, my OS is computational ethics, and the apps that instantiate that are cultures, institutions, and individuals. So we get a very full picture from observer theory across not just his categorical model for an observer. If you start to apply it to things, you get to say things and get to create a coherent narrative that pulls together the threads of so much disparate empirical research into a sort of a coherent story of what's going on. I think it's quite powerful because you don't have to use new axioms or new math or invent functions with weird stuff, which is what I think you see in a lot of a lot of people.
And I want to emphasize
I get sent lots and lots and lots of kind of theories of everything after that talk.
No, I'm sure. I'm there with you. But I was going to emphasize this for everyone watching, which is that this you've presented a really nice kind of verbal narrative, but this is not just this. It's actually, there's a whole mathematical framework you've worked out behind this to show how these things all fit together. So it is not just like a story you're telling, but it's like this is based on the math of Stephen's Ruliad, right? Like how that works. Now, the functions that I'm generating for how these specific subparts work might not be perfect. It might not be perfectly right. There may be better versions. And in fact, literally this paper, the first paper says, oh, we should use something like a K complexity measure for this. That turns out not to be right. But the structure, the architecture, the scaffolding of it is still right. Because I'm now going to put in a measure that I can use, which is finite from this paper, and I will update that the measure for that entropy and that sort of structured information based on that. So it's really, the way I'm thinking about this is, if I have this Ruliad as a giant box and this giant box doesn't have any structure to it, how can I give it structure for observers like us to probe it and do things? Now, these are the buckets or the categories of things I think you can do with it. And I think they're coherent and they work, and they don't currently break the formalism in the mathematical formalism or break physics, which is why I think it's important, is because you don't often see things that talk about ethics or telos that can directly link to a physics theory. And that is unusual. And I think that's why it's interesting, because I'm introducing one axiom. I think the couple of axioms in this are the Ruliad is a real thing. Okay, so lots of, a niche amount, but a lot of researchers are working on it. And then the other one is observers maximize integrated or structured information. That's it. Those are the two things. And then, I think the thing about observers having finite computational power is an empirical fact. Finite persistence time is also an empirical fact. And that observers make choices based on what they deem relevant. For observers like us, at least, and certainly for animals, and maybe even for plants, that is also empirical fact, even if you have the philosophical argument about whether free will exists or not. Here it's compatibilist. Yeah. Here the free will model is compatibilist because of computational irreducibility. And then I don't know if you want to go through this, but there's some stuff on theology in here. And this is like how I think, well, I'm curious. So, I mean, first off, I think your key metric for ideas that stood out to me was causal inference per computational cost. So if you have a minimal set of axioms that can link all these things together, then I hope your ideas catch on more quickly and people find them elegant with a high degree of explanatory breadth.
That's I think this is an explanatory conjecture. Everything is explanatory. Like I care little for ideas that don't explain something that isn't well explained. And I think I take that kind of beginning of infinity view of like the job of philosophy, science, math is to explain things. I know that's that's what this is trying to do. And it's been, I've never written, this took the work for the first paper took 1.5 years because I had to learn the formalism, and I've, the first version, you can ask CATM, was not very good. And so it's been an iterative process where I've been very lucky to have exposure to people like James Wiles at the Wolfram Institute and Xerxes and Stephen, saw him a few months, I saw him when he was in London. And so I'm very lucky that I get to test these ideas against people that will tell me if it's overreach or if it's stupid. And so the maths in this paper, I worked on it with a guy who's a sort of PhD AI researcher called Ali Osbey, who was fantastic and helped a great deal on formalizing some of the sort of structural maths of this. And then it's been surprising because, I've had engagement from, some world-renowned scientists, people that I hugely respect in academia. And what I've been pleasantly surprised about is people have engaged with the breadth of this, but also engaged in parts. So certain people were looking at this from just the 47-page thing that you looked at, from just this scaffolding might be useful for how I think about this, and this. And then other people have been very interested in what this is saying about, how you can model theology. Like you can model metaphysics now computationally and talk about what it's doing. And I've also had, people in sort of religious traditions like Christianity and Judaism and Buddhism go, oh, this is quite useful. I could do the mapping for and that's been really interesting and is kind of what it's for, right? Like I really, I'm not trying to give the final answer because there is no final answer. There is no objectivity at the very end of the day.
There is a final answer in your theory, but that's at like the end of time or something.
Yeah, it's at the infinite end of time. We're not there. We're not getting it. Don't worry. For us, there's always more to know. But this is about how to give lots of answers with the minimal set of brute facts or axioms. How do I give a lot of, and because Stephen's meta model is the biggest possible language structure we have, computation is the biggest object we can probe. It's bigger than math. It's every math. Every axiomatic math system sits in a computational universe. Like every single one. And Jonathan Garrardi, in fact, like today, posted like a 15.
Okay, well, I'm just going to point out though, but doesn't that imply that not all truths are computable?
Yeah, it does apply that, but we're not saying that everything in here computable by us, right? That's the point, right?
Well, no, but that's the Gödel's incompleteness theorem, right? Is that you can't have a full axiomatization that can prove all true theorems. Yeah,
but this is it's built into the structure, into like that sort of this infinite structure. You can't get to the final answer. Every system we have is ultimately limited by computational irreducibility, which is like the proxy. And here it's not the more important theory is Tarski undecidability, because that's directly related to the language, right? So Tarski undecidability is really the computational, at least it's not quite equivalent, but I call it weakly equivalent to like Gödel incompleteness in computation. And that is driving this structure. So yes, you can't get everything, but also a lot of those maths that we can't compute over, we can't agree on, we can't get to, we're too far apart in radial space. So this gives you some proxy for like, we will always not know something. And that is, and this is what framework can we use, which is the biggest we have so far, to make truth claims, or and whether my truth claims are right or wrong is almost beside the point. I think my instinct is that most theories should be framed in this sort of language, period, because you can be distinct, you can make them computable, at least in a toy model version, and you won't get perfect answers, but you'll get to the extent that you have computational power. And this is where we are in the world with LLMs and with AI and with AGI development. We are going to get something, we've got something already that can make more connections between the maps or the limits we've already got to than we can. And so we should be utilizing things like that to place objects and theories within this sort of universal language of computation until we get something better. And that's it, really. Yeah.
That's amazing. Dude, thank you so much for joining. This is awesome. I mean, there was a couple questions from the audience in real time. By the way, there's 1,000 people watching this right now, so that's pretty great.
That's cool, man. That's fun.
Yeah, that's great. That's great. A couple people were asking, do you see a link between Dr. Michael Levin's work? I mean, I think you answered that yes directly, and then but they also asked for Lee Cronin. Lee Cronin, assembly theory.
Yeah, so like when I mentioned that materialist scientist I speak to, like,
nice.
Okay. So like to be clear, right? My respect for these people is off the charts. Like people like anyone like in constructivism, in my view, they are the future of physics. Like David Deutsch, Yara Marletto, Lee Cronin, Sarah Walker, Stephen, Michael Levin. They are just phenomenal minds, and like no matter how much they all moan at each other and like this person's not right and he did, and I've heard them talk because I've gone like spoken to them, like they are brilliant, and without all of their fundamental work in the sort of, I'd say, slightly more disconnected ideas, like especially constructor theory, because this is like rules in the Ruliad are basically possible and impossible transformations, right? So this is like how I see it, and to me, like that work is going to be the work that moves those sciences forward, and whether or not Lee thinks this is a valid theory or not is is beside the point, because in my view, assembly theory is like a subset of this computational model. I mean, he literally like, we should compute chemistry. I'm like, and this is the computational meta model. Good, you should slot it in here. But I think he gets slightly upset because he thinks that stuff emerges still, and it's all bottom up, and I'm a bit of a top down. I am, and I think philosophers don't like it because they like hate metaphysics, or at least practicing philosophers do. Though to say that, I've been from doing the Platonic Symposium, I was the only independent researcher that wasn't like at MIT or Stanford, or
well done. I mean, it's really impressive to produce new ideas that would challenge their thinking and get them to think outside the box.
Yeah, but like I just want people to. I'd rather it be bashed. Like, I don't care. I'd rather, what my dream is, like, someone says, hey, this is totally wrong because these fundamental things are wrong here. And then this is right. I just want to get to truth. I don't want to be right to be right. I don't care. I don't, I'm not an academic, I don't care about, peer review or which journal publishes me. I run a fucking hedge fund. Like I have
that's awesome.
I care in the abstract because I get to push how hard I think in a way that is invigorating and fun, and also hopefully I get to do something that, this work, why am I doing this sort of work, right? Like the reason I'm doing this work is because I think, and it started from, we are telling everyone meaning, value, hierarchy, good and bad is all constructed. It's all social constructed. It's deconstructed. We've been telling people that for 70 years, and it's not working. And it's not working because we've gone off into sort of echo chamber pockets. And it's not that those echo chambers in physics, for people that are still working on string theory, are not producing high quality, good work. It's just that no one is bothering to join up all of these like big branches of the tree. And we now have a tool where we can join them up. And you might not like it, but if your theory has a computational angle to it, if it's computational, it should be able to be joined up in this box. So I know that you want to hold on to your thing, but we will get more from the network connecting than we will from pushing the boundary of like, the hundreds of papers on archive that are like, here's a tiny bit of the edge of this theory, and here's one construction that 5 people are going to read. Like, we should be excited as humanity. We shouldn't be negative. We are at like this transition point where, things are going to get a bit messy, but we are giving ourselves like an upgrade right now, and we should be leaning into that. And I think we're coming into like if we can get over the fact that the quality of our politicians is absolutely dire right now across the world, and we can actually get rid of these boomers, get some like good maybe slightly older than millennials, and millennials going, hey,
yeah.
all these problems, like, then we can actually do things. Like, you can just do stuff. And if you actually do the work properly, you can do it. And I wanted that for my son, who's 3 years old, because I wanted him to grow into a world that's changing rapidly, but where he knows that things matter, that value is real, that like the relationships you have, like, they are from a lineage and they are from things that matter, and you will always matter. Like, your life has value, everything you do has value, every choice you make has value. And to me, that's the underlying reason for doing this. Like, it's about family, it's about giving an alternative viewpoint to what I think is now turning into a poisonous philosophical top-down driver in our discourse, and it's just not working. So here's a better version, and I'm sorry, that's the only thing I'll claim is better. This is better than postmodernism. There you go. Like,
it's
better than a bunch of philosophy from a bunch of French guys that want to smoke fags and have sex with teenagers. That is postmodernism. I don't get to say that, but this is on X, so that's fine.
I can confirm that those criticisms are mostly true. Well, dude, thank you so much for taking time to present. I really do appreciate it. I think the comprehensive breadth and the touching on these very, very disparate fields with a high degree of elegance and I think conceptual leverage. I think there's ideas in here that I find very useful for myself. Like, I just see the connections right away. So I really commend you for the effort. And I'll just do a quick shout out. Where can people find more of this? Where can they learn more about your work or reach out here?
Twitter tag just up here. So, like, I am pretty bad at social media. I actually do some work, and want to give a shout out to a guy called Defender, who runs something called ORI, which is the Open Research Institute. They focus on memetics, and they were exceptionally useful, particularly in reading early drafts of the paper. This presentation is based on a 300-page paper that is an extension to that 47-page paper. And they were exceptionally helpful. And so I want to say thank you to them. All of my work is posted on my X profile, which you've kindly put in the thing. If you click on the pinned tweet, it will take you to the GitHub, which contains the paper, this presentation, and the 2 videos. And if you send me a recording, I'll also put this video up there of the ones I've done so far. And then I've just started a Substack. The Substack is called Observer Theory, with no spaces. And it's basically taking ideas from this and just applying it to lots of different things, and kind of more of a pop sci, less math, just to give you the ideas and the structure applied to things like meditation. So computational model of what you're doing when you meditate, like a discussion of like the idea war and how ideas, if I anthropomorphize or make the ideas more alive, what are they actually doing? How are they competing for your attention? What are we maximizing for? And I'm going to be writing every weekday a free post, which will probably be like a 10 to 15 minute read that will be on some subtopic of this overall paper, and apply it to, I just wrote, today I published something on that epistemic complexity and how it overlapped with observer theory in that Substack. And if you want to subscribe to that, look, I'm terrible at social media, so I really appreciate anyone liking, subscribing, sharing, because I am not built for it, and I'm not built for that world.
Well, that's good. Well, I mean, that's kind of why I'm starting this show, exactly for this kind of thing, cool ideas and help them get out there. So I hope as you work on these ideas more, you'll rejoin, come back and share more. And of course, open invite to come to Deep Tech Week anytime. It's in a few different cities this year. So this is exactly the kind of thing.
You got my number, man. Send me a message.
Yeah.
Look, I've got a young toddler and a lovely wife. And so I get to buy every year. I get to buy a couple of conferences, which I get invited to go and to go away. So I would love to do that. It'd be great fun.
Awesome. Thanks so much for joining, man. Good to see you.
Andrew, appreciate it, dude. Have a great night. Bye.
All right. Okay, that was awesome. Theories of reality, ethics as a operating system for reality, and how it emerges from the computational nature of the universe. I think this is a really interesting topic. And I mean, I think I'm going to keep exploring. Maybe we'll keep Fridays for philosophy. But so far the week, we had Monday was platform therapeutics and personalized medicine. Tuesday, we had synthetic fuel production and, the Fischer-Tropsch process and geothermal for synthetic hydrocarbons and sustainable aviation fuel. Wednesday, we had electrostatic inertial confinement with avalanche energy. Thursday was quantum mechanics and the Einstein-Podolsky-Rosen paradox. And Friday was a new theory of everything. So this is a good breadth. It's good breadth. We'll keep it up. Next week, we have some more guests coming on talking about reversible computing, geoengineering, as well as quantized inertia, which may be a new theory of gravity. So if people are interested in presenting, I'm always happy to give a voice and a platform and an audience to people that are working on cool stuff. It can be in hardware engineering, it can be in biotech, in computing, it can be in foundational physics and philosophy. So please reach out. I'm very accessible on Twitter. And thanks for joining. See you next week.